Yeah, we're going to do the impossible today.
Great.
We're going to prove something in constant space, whatever you want. Um, Asterisk. Okay, so welcome back to the crypto seminar. Last week or last time, we sort of wrapped up our discussion of the more theory side of things with non-interactive proofs and so on. And today we're going to look at we're going to zoom in on an application of zero knowledge proofs. So, uh, what have we done? We have proved that every NP language has a zero knowledge proof. That's very good. We like that. But we have two important limitations, right? Problem that we have is uh, the first problem that we have is that the protocol is interactive, and there's no obvious way to fix that. Our Fiat-Shamir transformation only works for Sigma protocols, and the reduction that we have, or the construction that we have for graph 3 coloring is not a Sigma protocol. So that's problematic. Protocol is interactive. And why is that problematic? Well, it's just often infeasible, right? You don't want, oftentimes when you want to have a zero knowledge proof, say like a signature system, a digital signature system can be thought of as a type of zero knowledge proof. You don't want to force the players to, the parties to interact online every time you want to check a signature. So that's a pretty key limitation. The second is even worse, and that's that the proofs can be really expensive. So first you have to do the NP reduction, and then you have to actually carry out the graph 3 coloring proof. And that proof can get extremely big extremely quickly. So the proof can be extremely expensive. And that's both in time, in how long it takes to check the proof, and also it can be in space, that the proof itself is just an enormous amount of memory. And we're going to fix both of those problems, or all three if you like, because we have time and space. We're going to fix all of those. So we're going to talk about, by now it's a bit of an old construction. It's from 2013, but it's sort of one of the simpler constructions and one of the more well-studied. So we're going to see how this works, with the caveat that this is not as efficient as it could be. There are lots of cleverer ways to achieve the same goal. So we're going to talk about SNARKs today. What is a SNARK? It is a succinct, I can't spell. It's a succinct, non-interactive argument of knowledge. Okay. So we know what a proof of knowledge is. This is a proof that I know some, often that I know some satisfying assignment to an equation. For example, I know the discrete logarithm of some group element with respect to a fixed generator. And the way that we defined this was sort of this indirect approach using an extractor. We're not going to really revisit that today. This is going to be a more high-level discussion because really proving that what we are going to construct is a proof of knowledge carefully is a long and complicated process. So we're just going to see, at least today, we're going to see the higher level. Okay, so succinct, what does this mean? It means at most log n space and verifying. Okay, where n is some security parameter for the problem. Okay, so we definitely don't want quadratic space and verifying time. And ideally, we want to do better than linear. And the argument part, this is something that I haven't really talked about in the seminar so far, but the point is that there is a non-zero soundness error. Okay, that's why it's called an argument and not a proof. It's a negligible soundness error, so there's a negligible chance that you might be able to produce a snark that you know something when in fact you don't. Negligible chance, but non-zero. That's why it's called an argument, not a proof. That's a technical detail. It's not terribly interesting. So the snark construction, we'll see, it doesn't quite do NP, but it has a very, very wide range of applicability. or being non-interactive, and remarkably, we can do it with logarithmic or even constant size proofs. Now, this is really quite a strange thing to claim if you think about it. How on earth am I going to prove that I have how am I going to prove that I know a discrete logarithm of some enormously big group element in constant space? That doesn't sound like it should be possible, and yet it is. So we're going to see, I'm going to go through the two key gadgets of this construction. It's a bit complicated, as we'll see, but this is maybe not terribly surprising. But it should make sense. It's the sort of thing that's complicated, but not beyond the grasp, if you like. So we have two key gadgets. We're going to use arithmetic circuits. And we're going to use at least a kind of polynomial commitment. Sidebar, if you want to translate a really general statement into a SNARK, there's another step called a rank 1 constraint system. We are not going to talk about that today. Hopefully you're satisfied with the more limited perspective that we take in the interest of expediency and also not being horrifically complicated. So what's the path that we're going to do? We're going to take our statement that we want to prove, knowledge of something, and we're going to translate it into an arithmetic circuit, which I will define in a minute. And then we're going to define it, and then we're going to translate it into equations of encrypted in air quotes because that's sort of vague, polynomials. And then we're going to evaluate the polynomials at one point. Now, if you know a little bit about polynomials, you might see where this is going, but I won't spoil you if you're not quite sure yet. This is going to constitute a sound proof of, or a sound argument of knowledge. Just evaluating at one point is enough. Okay. So let's dive in. Okay, we have arithmetic circuits. What is an arithmetic circuit? It's a model of computation of a kind that is not quite Turing complete, depending on how you look at it, but has plenty of flexibility for the sake of cryptography, in particular because often in crypto we're interested in proving that we know some satisfying assignment of an arithmetic equation in perhaps some finite field or some group, right? So if we talked about this before, that to prove knowledge of, say, an Al-Gamal private key, that's of the form y equals g to the x, where x is secret. And we might wish to prove knowledge of this x. Okay, so a lot of crypto statements can be translated into arithmetic circuits. The details of how to do this get complicated, but hopefully you believe me that at least this is a sensible place to start. So we're going to fix some prime p. And we're going to consider everyone's favorite finite field, fp. So our running example is that we may wish to prove knowledge of a few variables, C1, C2, C3, such that, say, C1 times C2, these are in the field, times C1 plus C3 equals 7. This is a contrived example. Because of the nature of how we use field operations in crypto, a real world example is going to be like extremely big, and I'm not going to be able to really draw it. So hopefully you can take my word for it that this contrived example nonetheless contains the key ideas. So we're going to do something a little bit strange. We're going to draw a graph. Okay, we're going to represent this equation as a graph. So the idea is I have input nodes. These are my variables, C1, C2, and C3. And I'm going to draw essentially a syntax tree, right? So here I have C1 times C2. So I have a multiplication node of my graph here. Here I have C1 plus C3. So I have an addition node here, or an addition gate, to use the digital circuits analogy. And I'm going to draw edges in the graph that show, okay, C1 goes to times, and it also goes to plus. C2 goes to W2, C2 goes to times, rather, and C3 goes to plus. That is very difficult to see. It's better. And what are we going to do once we've multiplied C1 by C2? We're going to multiply it with C1 plus C3, so there's another multiplication gate up here. Okay. So the idea is I'm going to label each of these edges with a weight of some description. This is meant to indicate the value that it's carrying, right? So these blue edges at the bottom here are both carrying the value C1, and I'm going to think of this as one wire because it's transporting the same value. It's one wire, and I'm going to call this W1. This red edge here is carrying the value C2. That's a different value, so I'm going to call this wire W2. And again, the same with C3. This is a wire W3. Now, I have a multiplication at the top, so this is going to be wire W4. That's equal to C1 times C2. And both for reasons of efficiency and also the construction, remember we want to turn this somehow into polynomials, we're actually going to sort of pretend that addition gates don't exist, okay? And what we're going to do instead is say that this wire contains as inputs both W1 and W3, okay? Because C1 goes to plus, so does W3. So we're going to think of C1 and C3 as two inputs on the right of this multiplication gate. I just draw it as a separate node to help us not forget that that's what's going on. So I don't actually need a fourth wire for this red edge. And the last thing is, once we multiply, there's going to be some value at the end, and we'll call this a wire W5. Okay. Any questions about this picture that I've drawn?
Yeah, I'm a bit confused by this latest comment. So then the X at the multiplication node at the top will have, in that other view, three inputs, two of which I add together, and then I multiply them with the third one. But how am I supposed to know what to add and what to multiply? Oh, I see.
Yeah, so
I think of it as a single input.
That's right. You think of it as like you can think of it as a single input, or you can think of it as two right-hand inputs, which are always added. So okay. you only label wires coming out of multiplication nodes or inputs. The addition ones come together, and this will start to make sense when you this sounds a little bit strange, and it will start to make sense as you realize we want to translate this into polynomials. It'll start to make sense why we did it this way. Yep.
Yeah, I'm looking forward to that part.
Nice. Okay, so I'm going to define some terminology. A legal assignment is a tuple my undo is this. A tuple C1, C2, up to C5 of values for each wire. Note that I can just as well, these C's that I've written here, I can just as well think of them as wires, right? Because they have a wire connecting them. So I can think of C1, C2, C3 as wires that I'm giving the values C1, C2, C3, and I'm also giving values to these last two wires. That's why I've overloaded the C's here. So it's a tuple of values for each wire. such that the equation is satisfied. Or the equations, there are multiple, are satisfied. So in particular, we have, I've got W4, that should be W1 times W2. So that's one constraint. C4 equals C1 times C2. I similarly have W5 or C5 is equal to C4 plus C1 times C3, W4 times C4 times C1 plus C3. Okay, and again, because we're thinking of this red wire at the top right, we're thinking of it as one single thing. So that's why we have the multiple terms here. This is C4 times C1 plus C3. Okay, these are the equations that or the constraints that our graph has. And we want to, what are we trying to prove in our SNARK? We're going to prove that we know a legal assignment such that C5 is equal to 7. Okay, and hopefully you are convinced that if we can do this, then we have indeed proved knowledge of C1, C2, C3 such that this equation holds. Okay, so we've converted, we've got this nice graph structure, and we know what we're trying to prove. And let's see how we can transform this into some polynomial equations. Okay. So why polynomials? If you like, a polynomial contains an unbounded amount of information, right? Because it has an unbounded number of coefficients. So we're going to use this feature of polynomials, or abuse this feature of polynomials, to reduce proving this knowledge into proving knowledge of some polynomials, and then we can exploit linearity and so on to produce our final proof. Okay. So I'm going to define some polynomials based on this graph. Left wire polynomials. L1 to L5. I'm going to have some right wire polynomials. R1 to R5. And I'm going to have some output wire polynomials. O1 to O5. Okay, so we have one polynomial per wire, and notice that there's a loud noise outside, sorry. And notice that we have the same number of each, so we don't have 5 left wires. What are we going to do? Well, we're going to set those polynomials to 0. Okay, so our constraints, we want it to work out so that, I've forgotten to label something else on this graph. The graph on the left, we're going to label each multiplication node with a G, so in this middle board. So that's G1 and that's G2. Okay. What we are going to do is assign each multiplication gate a target point in the field. So the first multiplication gate G1, I'm going to assign it the value 1 in the field, very creative. And the second multiplication gate, I'm going to assign it the value, you guessed it, 2 in the field. Now the idea is the multiplication gate G1 has as inputs W1 and W2 and output W4. So I'm going to make L1 equal to 1 at G1 and 0 at the other g's, okay? So the polynomial is selecting, in some sense, which gate this left input corresponds to. Okay, so I'm going to set, I have, if I draw the gate here, I have G1, and on the left I have W1, on the right I have W2, as output I have W4. So I'm going to set L1, the left input, equals R2, the right input, equals O4, the output. And I want this to be 1 at G1 and 0 at G2. How do I do that? I make this 2 minus x, okay? This is in, of course, FP adjoint x. Okay, so I'm matching the indices of the left, right, and output wires. Any questions? This is a little bit, this step is crucial, so I want to make sure that this is clear.
Yeah, I didn't quite get, I suppose I get, what's the, making it attain some values at G2. What does that mean? So you want it to be 1 at the place where it's defined and 0 everywhere else. Oh, and there's no G3 because that's a plus, and pluses don't count.
Right, exactly.
Yeah, okay. So
only the multiplication gates that we assign.
Okay, yeah.
And you could do, if you wanted to, something like Lagrange interpolation, right, to reduce these polynomials.
Right, and you just pick some arbitrary different values at all the multiplication nodes.
Right, exactly. I mean, the values don't have to be different at the different multiplication nodes. They just have to be 1 at the one that they apply to. Yeah. But you can make it work exactly like that, yeah.
Okay.
And in the other case, I have G2. As input on the left, I have W4. As output, I have W5. As input, I have the addition gate made up of...
You wrote L2 of G2 as 0. Did you mean L1?
L1 of G2, I did indeed. Okay. As right inputs, we have the wires W1 and W3 via an addition gate. So we're going to set L4 is 1 at G2 and 0 elsewhere. So is R1 and R3. This is what I mean by viewing it as having multiple inputs, right? You have the right inputs W1 and W3, which means that R1 and R3 are going to be 1 at this point. And that's equal to O5, which is equal to x minus 1. Of course, this is the correct polynomial, right? It's 1 at G2, it's 0 otherwise. And then we just set all of our other Li's, Ri's, and Oi's to be 0 otherwise. So now I have a whole collection of polynomials. I have, for each wire in my diagram, I have 3 polynomials. And we want to somehow encode this constraint, the constraint that I mentioned on the left, the legal assignment constraint. How are we going to do that? Well, we want our polynomials to, what we're going to do is we're going to define polynomials weighted by our assignment values, and then we're going to produce a polynomial that vanishes on G1 and G2 if and only if the assignment is a legal assignment. Okay, so we're going to weight each Li, Ri, Oi by the Ci's. So we define L to be the sum of Ci, Li. Remember, the Ci is the assignment that we are checking if it is legal. So that's C1, C2, C3, C4, C5. R equals Ci, Ri. O equals the sum of Ci, Oi. So what are we supposed to be doing here? We want the multiplication of the left and right polynomials to be the correct values of the Ci's. The correct values are included by the O. So we define our overall polynomial to be LR minus O, which vanishes at G1 and G2 if and only if C1 dot 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 C5 is a legal assignment. I'm going to do the concrete example so that you believe me. Okay, so in what do we have concretely? We had L is equal to C1 times L1, which was 2 minus x, plus C4 times L4, which was x minus 1. So what's L of G1? That's L of 1, remember, which is 1, C1 rather. L of G2. Clever. It is very clever, isn't it? C4. Let me finish, Dan, before you give away any more. What's the right polynomial? It's C1 times R1, which was x minus 1, plus C2 times 2 minus x, which was R2, plus C3 times x minus 1. What is R of G1? That would be R of 1, obviously, which is C2. What's R of G2? It's C1 plus C3, which indeed is the right input to our second gate. So what is O? That is going to be, I've messed up my notes slightly, but it's C3 times x minus 1 plus C4. Maybe those of you who are not as incredibly clever as Dan are starting to get where we're going with this. O of G1 is C4, O of G2 is C3. So what's LR minus O? Well, I'm not going to write it out because it's a big, ugly polynomial, but P of G1 is going to be, of course, L of G1 times R of G1, which is C1 times C2, minus O of G1, which is C4. Remember, we want C1 times C2 to be C4, so we've encoded it here. P of G2 is C4 times C1 plus C3 minus C5. So we've now encoded our equations into we've encoded our equations now into evaluations of a single polynomial at 2 different points, one for each gate. Okay, marvelous. So somehow we've got all these constraints, but we have one single polynomial that covers everything. And I want to do one more little thing for the sake of producing our zero knowledge proof. I'm going to also define t of x, and this is the target polynomial. I don't have a good intuition for the name, to be honest, but it's describing the shape of the graph somehow. So it's the product of x minus gi's. And the idea is that t of x divides p of x if and only if ci is a legal assignment. Okay, that's just because we want it to vanish on the points ci, so it vanishes on the points gi, so it vanishes on the points gi if and only if t divides it. Okay, all of this is called, has a special name. I didn't have space at the bottom. It's called a quadratic assignment program, quadratic arithmetic program. So what I mean by all of this, well, it's the LIs, the RIs, the OIs, and T. So we are going to prove that we know a P of X that satisfies the quadratic arithmetic program. Okay, a solution to a quadratic arithmetic program. And this is how we are going to produce our proof. Okay, questions?
I like it. No questions.
I thought you might. Seems a bit up your alley, Dan. Okay, let's keep going. So now we have to figure out how to prove knowledge of a solution to a QAP. We've shown that this is going to be equivalent to proving knowledge of a legal assignment for an arithmetic circuit, which covers a whole range of stuff that we like to do in crypto. So the protocol that we're following is called Pinocchio by the authors Parno, Howell, Gentry, and Reykova.
That's Gentry as in
2013.
homomorphic encryption Gentry.
That's the one. So, okay. We're still a little bit stuck on where to go here. We want to keep P of X secret and yet show that it's the right polynomial. And yet somehow show that we know it, that we know a polynomial that really does satisfy the constraints. And worries me, I did not write down the name of this lemma. Dan, help me out. You know the lemma that says that two polynomials are equal at a random point almost never if they're different?
No, I don't know the name of that. Sorry.
Damn it. I've just realized that I didn't write this down. Well, the idea that we're going to use is if I take two polynomials that are not equal and I just pick some random point to evaluate them at, they are almost certainly not going to be equal at that point, right? They're only going to be equal at that point if you can do this by the information theoretic argument. There are so many values that it could have, and they certainly can't coincide at more points.
Well, its vanishing set will be lower dimensional, so it's measure zero.
Exactly, that's right. It can't possibly vanish at that. The difference can't possibly vanish at that many points. So this is the idea we're going to do. We're going to evaluate it at a single point chosen at random, and with overwhelming probability, the prover will not be able to produce the evaluation that they need. To do this, we have a slight problem. The verifier wants to choose a random point and then get the polynomials evaluated at that point. But if the prover knows the point that was chosen, then they could possibly engineer some polynomials that happen to vanish on the correct things. So we have a situation where the prover is going to produce P of S without knowing S. S, and the verifier has to be sure, has to be convinced, I'll call this Y equals P of S, Y was correctly calculated without knowing P. Because if the verifier knows P, then it knows the constraint variables, the assignment C1 to C5, which is exactly the thing we want to keep secret. So we're a little bit stuck, and we're going to use a gadget called, we're going to use homomorphic commitments. The more modern approach uses something a bit more general than this called a polynomial commitment, but we're going to be looking at a special case of polynomial commitments where you can do blind evaluation. So we'll explain what this means. The idea of a polynomial commitment is you're going to give me some value called commit of P, and then you can prove that P of X equals Y without revealing P. So the idea is you're going to give me some commitment. I say, give me the evaluation at X, and you're going to go, sure, here's the evaluation, and here's proof that it really is the same polynomial I committed to, but you don't learn what the polynomial you committed to is. We're going to do something, we're going to do a little bit more of a special case, and we're going to use what's called a homomorphic commitment. I won't have time to look at the details of this today, maybe next time, depending on interest. TLDR, the easiest way to do this is using the Tate pairing on elliptic curves. I don't know if that means anything to anyone listening, but that's the trick. So I've got some secret value in my field, or some secret value in my field, and I produce a commitment such that the commitment gives no information about S. How is that defined? It's defined in terms of reduction. We say that we say that assuming taking some assumptions, such as inverting a pairing, is hard. You show that no efficient program can correctly guess the value. This is called hiding, the hiding property. And you can do the commitment is a homomorphism, a ring homomorphism. So given com of S and com of T, you can calculate commitment to S plus T and a commitment to ST. The classic Pedersen commitment, which is sort of the standard way to do commitment, it's a group homomorphism, but it's not a ring homomorphism. You only get the additive property. So we do need some slightly fancier math to produce such a thing, but you can take my word for it that it's possible. Okay, so we're going to do this blind evaluation. I label this blind evaluation. We can use this gadget to do blind evaluation. We are going to need a slightly strange difficulty assumption to do this, which I will write on the next board. Knowledge of coefficients assumption.
To the extent I understood it, the homomorphic, I don't know if that's the same as homomorphic encryption. It looks like it's
same idea, but it's a commitment instead of encryption.
Is non-trivial. Is the polynomial commitment story strictly more
highly
complicated?
Non-trivial as well.
Yeah. Okay.
Yep. The standard ways. There are other ways to do it. The standard ways to do either polynomial or homomorphic commitments involve elliptic curve pairings. This is sort of the canonical way to do it. And this is a whole bunch of fancy number theory that I only barely understand the basics of.
I guess that wasn't the part that scared me. It was the kind of recursive stuff where you're encrypting. I forget exactly how it works, but there's like encryptions of encryptions of encryptions or something, like some crazy recursive scheme in homomorphic encryption.
That's not too bad, honestly. The actual commitment schemes are not.
We disagree on
the commitment schemes are not. The commitment schemes themselves are not that complicated technically. They're just very complicated mathematically.
Okay.
The recursive constructions that you're talking about are weird, but they sort of just fall out of the construction that you do here. It's sort of, maybe that's another topic. That's a topic for the future, that you can do recursive zero knowledge proofs, right? I prove something, or I have a sequence of things that I want to prove. So I prove the first thing, and then I prove the second thing plus knowledge of a proof of the first thing. Then I prove the third thing plus knowledge of a proof of the second thing, and so on. And by induction, I give you one proof that proves knowledge of a whole sequence of things. That's a recursive SNARK, which is crazy.
That's so cool.
Maybe a topic for the future.
Yeah, okay.
Okay, so this knowledge of coefficients assumption, the idea is the verifier is going to send a bunch of commitments to the prover, and the prover is going to reply with 2 commitments, and then, except with negligible probability, that means that the prover must know a linear combination of the stuff that we committed to. That's an assumption. That's a hardness assumption, of course. Saying that anything is hard is going to be some kind of assumption, because we don't have P doesn't equal NP. Okay, so it works like this. If Bob chooses secret S from the field uniformly at random, and a secret from the units uniformly at random, and sends to Alice, we're going to send a bunch of powers of S and alpha S. Okay, so I'm going to send a commitment to 1, a commitment to S, up to commitment of S to the power of D, where D is the parameter. It's just the degree, that's why I call it D. Sometimes you'll hear this called DKCA. Okay, I'm also going to send powers of alpha, so I'm going to send, or more accurately, I'm going to send, you'll see, a commitment to alpha, a commitment to alpha S, to a commitment of alpha S to the D. And if Alice manages to respond with a commitment to A and a commitment to alpha A for some A in the field, doesn't matter which, then it must be the case, except with negligible probability, must be the case that knows LS knows, my notes have gone to sleep, C0 up to CD, such that A is the linear combination weighted by Ci of S to the power of I. In other words, Alice proves that she knows some polynomial such that A is equal to P of S by computing, I'm going to write this down, Alice knows some P in polynomial ring that A equals P of S. And what does Alice compute? Well, a commitment to P of S is a commitment to C0, where the CIs are the coefficients of P, plus a commitment to C1 times a commitment to S, which is given by Bob. I will underline the stuff she's given by Bob in blue, plus a commitment to C2 times a commitment to S squared. This is the homomorphicity property, yeah. I can compute these, I can compute the commitment on the left-hand side of the equals by multiplying and adding the stuff I know, plus so on. And she can also compute alpha P of S by multiplying the commitment to C0 by the commitment to alpha, plus the commitment to C1 times the commitment to alpha S, plus the commitment to C2 times the commitment to alpha S squared, and so on. And what does Bob do? Of course, Bob gets a commitment, a black box commitment. He doesn't know what it is, but he can multiply it by alpha. Yes, let's say B equals com A, and checks that alpha B equals the commitment to alpha A that he was expecting. So Bob's just checking that he's got two commitments, one of which is the other times alpha. And this proves indirectly, according to the KCA assumption, that Alice knows some polynomial that is a linear combination of s's and alpha s's, of s to the n's and alpha s to the n's rather. Okay, this is a weird assumption, but I mean, this is what we have to do, right? We have to prove knowledge of polynomials. So if this looks a little bit sus to you, it looks a little bit sus to cryptographers too. There's a bunch of work that is not yet very conclusive on whether this is a reasonable thing to believe, but it seems to be. Certainly, there was a lot of money that someone could have made if they knew a way to break it on, say, Zcash and so on. So this seems to be an okay assumption. Okay, can I clarify anything? Yeah, so this is the blind evaluation protocol, right? Bob chooses a secret S, sends some commitments to Alice, and the Alice produces the evaluation of some polynomial at S while keeping the polynomial secret. So we can use exactly this assumption to do our blind evaluation. All right. So let's see how the proof actually works, the SNARK. So the public information that we have is the Li's, Ri's, OI's, and T that specify the quadratic arithmetic program. And the private input for the prover is some polynomials L, R, O, H such that LR minus O equals TH. That is, T divides P in the previous notation, and the quotient is H. And also, L is a linear combination of Li, R, Ri, O, Ri. In other words, the polynomials that the prover knows are indeed ones that you get by multiplying the Li's by the constraints and summing them up. So we have the right P that we're supposed to have. And they have to be the same, they have to have the same coefficients in each case. Okay, so it has to satisfy the equations that I wrote on the other board simultaneously for the same C1, C2, C3, etc. Okay, so part one is easy, right? Right. What do we do? P and the prover P and the verifier V use blind evaluation to get commitments com L of S, com R of S, com O of S, and com H of S, where S is secret and chosen by the verifier. And the verifier is just going to check that the equation is satisfied. Using the homomorphic property to do this inside the commitments. Okay, and because with overwhelming probability, two different polynomials don't coincide at a random point, this in fact constitutes a proof or an argument, to be pedantic, constitutes an argument that the prover really does know polynomials that satisfy this equation. the prover would have to get extremely lucky to choose polynomials that just happen to satisfy it for this one particular S and nothing else. So the prover definitely knows polynomials that satisfy this equation. Now the next question is, okay, but how do you know those polynomials have anything to do with the quadratic arithmetic program that we had in mind? How do we know that these polynomials actually do constitute a legal assignment to our arithmetic circuit? That's part 2. What we're going to do? Yes, Steph?
Yeah, but so this argument about measure 0 relies on being over an infinite field, which you're not. So there's a scaling thing here with the p or something?
Exactly, that's right. So p is exponential in your security parameter, right?
Right, okay.
So it's a standard crypto thing, right? P is exponential in your security parameter. So the probability that the prover guesses correctly vanishes exponentially fast as the security parameter increases.
Yeah. Okay.
Yeah. Okay. So what we're going to do is we want to. Really, what are we doing here? We want to prove knowledge of some coefficients that are the same for all 3 polynomials that satisfy some stuff. So the first thing we are going to do is combine the polynomials Li, Ri, and Oi into one thing. And then we are going to prove that we know a linear combination of this combination, and that will suffice, as we will see. So I'm going to combine each Li, Ri, Oi into one. How do we do this? Well, all we're gonna do is just shift the color coefficients around, and also show you what that means. Essentially, if you think of the polynomials Li, Ri, Oi as a list, we're just concatenating the lists, and that will give us a polynomial of degree 3, d plus 1. Okay, d plus 1 because there's the constant term s to the 1 dot 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 s to the d. That comes from the DKCA assumption. What do I mean by that? It's very simple. Fi is defined to be Li plus x to the power of d plus 1 Ri plus x to the power of 2 times d plus 1 times I. So now we have all the coefficients from Li, Ri, and Oi in one, and they're not going to interfere with each other because they're attached to different powers of x. So notice that if I sum up the Fi's, I get sum over Li plus x to the d plus 1 times the sum over Ri plus x to the power of 2 d plus 1 times the sum over I, so that if we define f to be the weighted sum with our assignment variables, this is going to be exactly sum of CILI plus x to the d plus 1 times the sum of CIRI plus x to the power of 2 d plus 1 times the sum of CIRI, which is of course exactly L plus x to the d plus 1 R plus x to the power of 2 d plus 1 O. So what do we have to do to prove that L, R, and O represent a legal assignment? The only thing that we have to do is prove knowledge of prove that this linear that this thing here, which the verifier can calculate by the homomorphic property, needs only prove that this thing here is a linear combination of the Fi's, exactly like this. That's all you have to do. So we can do this in a similar manner to blind evaluation. Now, the prover is going to choose, the verifier is going to choose beta uniformly at random from the units, and is going to send commitments com beta f1 of s up to com beta fm of s, where m is just the number of allies. Of course, the verifier knows this secret s, and the FIs are public knowledge, so the verifier can, of course, do this. And we're going to accept the proof, the overall proof, if P manages to respond with a commitment to beta f of s. How is the prover going to calculate this? Well, the prover knows beta f1 of s, so it can calculate a commitment to c1 times beta f1 of s, and so on, and then sum them up to get a commitment to beta f of s. How is the verifier going to compute this? The verifier knows a commitment to, from the first step, knows a commitment to L of s and R of s and R of s. So it can use star to compute a commitment to f of s, and thus a commitment to beta f of s, because it knows beta. That's it, that's the proof. So what have we done? What has the prover sent? Let's think about this very carefully. What has the prover sent in this entire proof? In part 1, the prover has sent 4 field elements. In part 2, the prover has sent 1 field element. So we're sending a constant number technicality. The codomain of the holomorphic commitment is usually not the field, but think of it this way. The prover has sent 5 commitments independent of the size of the quadratic arithmetic program, independent of the size of the statements. And if you do the math very carefully, you discover that these commitments don't grow that fast with respect to the size of the program. So the entire proof grows very slowly with respect to the size of the program using this clever arrangement of polynomial commitments. What we haven't discussed yet is zero knowledge. So that's the topic for next time. This is not a zero knowledge proof, but we can make it into one. Okay. I'm going to leave the body there as on a cliffhanger. Do you have any questions, Dan or Martin?
No, I think I have to think through the degree of the polynomial to believe your last statement there. But
which last statement?
Well, the fact that the size of the polynomial grows not so quickly.
I believe the version that I present here, I have to double check this. I believe the version I present here is actually linear size, but there's a lot of clever tricks involved that let you do better. I'm just presenting a version that is comprehensible. And even linear size is pretty good, much better than quadratic or worse, which you get with sort of more obvious constructions. But do you believe me that this is a sound proof?
Yeah, I think I buy it. It's very clever.
That's a victory for me. Martin, any thoughts? Okay, great.
Yeah, thanks a lot, Eleanor. I look forward to next time.
Thanks very much. Yeah, see you next time. Bye-bye.